Okay, this is stations 2 of the Wave Stations Lab, and I want to talk a little bit about how to solve wave equation problems so that you understand how to do that. They're relatively simple, but you have to remember a few things. Okay, so at the top of this, I put a wave just to show a couple things. I'm not going to go through the whole thing, but I do want to highlight a couple things. One is the wavelength here. For example, C is the wavelength. Okay, and you can see this wavelength is measured from crest of the wave to the next crest of the wave. Okay, just to give you an alternative, you notice this is the wavelength right here, right? Okay, and that's going to be in meters. Okay, there's another way. There are two other ways, that common ways of measuring a wave, and the other one is from trough to trough, and that's this one here. That's also the wavelength. You notice these are the same lengths, right? And then the last one is if you measure it from, say, equilibrium, moving toward the crest, then you follow the wave to the same spot at the end of that wave, which would be right here, where the wave is moving at equilibrium, moving toward the crest again, then this would also be the wavelength. Okay, and you notice this is again the same distance, right? Okay, so the wavelength is really, like it says, it's the length of the wave, and it's in meters. Okay, and so there is the wave equation basically says that the velocity of a wave is equal to the frequency of the wave times the wavelength. Well, the frequency is going to be in hertz, okay? And the wavelength is going to be in meters. And then the velocity will be in meters per second, okay? And so I'll talk a little bit about the frequency. The frequency is the number of waves, the number of cycles, the number of vibrations, the number of oscillations. That's all kind of the different words for the same thing that pass by a given point in a period of time. And we use hertz. So hertz is the number of waves, the number of cycles, vibrations, oscillations, all of that pass by a given point in 1 second. Okay, so in terms of that number, then it's a number, right? Or it's a number of cycles in a second, right? So what you're looking at then is like the number of these things, like this wave right here, it would pass by in some period of time. And you take that number and multiply it by the length of that thing, and that would give you a distance divided by a time. Okay, so that's how it all works. That's probably more detail than you really need, but that's basically how it works. Okay, so this next question, it says, well, find the speed of a wave with a frequency of 512 hertz and a wavelength of 0.66 meters. So the speed, so we're dealing with magnitudes here. We're not really dealing with direction. So this is just going to be a magnitude. So the velocity equals the frequency times the wavelength. Well, this is the frequency, right? And this is the wavelength. So you just multiply these things. Okay, 512 hertz. So this is very straightforward, right? Times 0.66 meters. Okay, and if you do that, do the math. Okay, do math. The answer, I'm going to round this, okay, is 338 meters per second. Okay, so that would be the velocity of that wave. Okay, now I want to talk about these two below, 2A and 2B, because they're kind of a special situation. Okay, so the best example of, say, a transverse wave is electromagnetic radiation. And electromagnetic radiation is commonly called light, right? So that's a transverse wave. So an electromagnetic wave, a light wave, travels in empty space, a vacuum like space, travels at a speed of 3 times 10 to the 8 meters per second. That's a constant. This is the speed of light. Okay? This is the speed of light. And in physics, the speed of light is c. So the speed of light is 3 times 10 to the 8 meters per second. This is on your formula chart. So I want to make sure that I'm clear about this. So this c, okay, is the speed of light. Okay? And that's what's mentioned here. The speed of all electromagnetic waves in empty space is 3 times 10 to the 8 meters per second. And for this class, for now, you should treat this as a constant. Okay? So why am I emphasizing that? Well, let's talk about two different types of waves, radio waves and visible light. These are both electromagnetic radiation. They're both, in a sense, light waves. However, they vary significantly in their frequency. Visible light is just like it says, light that's visible to the naked eye. Okay, you can't see radio waves. They're not visible to the naked eye. Okay, but you can see visible light. So what it's asking for here then is calculate the wavelength of these two waves. And they were emitted at the following frequencies. Okay, so let's do that. Okay, so radio waves, let's do the first one. So velocity equals the frequency times the wavelength. So we're looking to find the wavelength. Okay, that's what we're trying to find. Okay, well, the velocity then is the speed of light. 3 times 10, right, to the 8. And I'm not going to write the units. And then the frequency, okay, the frequency is 88. Times 10 to the 6. Okay, hertz, right, times the wavelength. Okay, so now all I've got to do then is take 3 times 10 to the 8th and divide it by 88 times 10 to the 6th, right? And that will give me the wavelength. Okay, and the wavelength for this thing is 3.41 meters. Okay, that equals the wavelength. So the wavelength of this radio wave, okay, is 3.41 meters. That, you notice that's a fairly long wavelength. Radio waves are a long wavelength wave. Okay? Okay, now that's a long wavelength, right? Okay, so let's look at a shorter wavelength electromagnetic wave, and that's visible light. Okay, so we'll do that down here. So again, visible light, it travels, its velocity is the speed of light. 3 times 10 to the 8. And that's going to equal 6.0 times 10 to the 14. That is the frequency times the wavelength. So then dividing these two again, okay, dividing these two out, here I'll circle the first one. There's the first one, right? Then dividing 3 times 10 to the 8 divided by 6 times 10 to the 14th, which you get then is 5 times 0.5, right? Now I want to change that to 5 though. 5 times 10 to the minus 7 meters equals the wavelength. And again, that is short wavelength or shorter wavelength radiation. Okay? As a general rule, as the wavelength becomes shorter, the energy becomes higher. And for example, visible light has more energy than, say, radio waves. And then something like gamma rays would have even more energy than that. Okay, so that's how you can find the wavelength. Remember that whenever it says an electromagnetic wave, if it doesn't tell you the speed, you assume it's the speed of light. Okay, assume it's the speed of light and use that in the calculation.